Okay, another example of a hypothesis test here. Here's the situation. We take a random sample of 49 observations. The sample mean we get from that sample is 8.5, and the sample standard deviation is 1.5. As soon as you see that, you know you're going to be using the t-distribution and looking up values in the t-table to do this test. Tells us to use an alpha level of 0.10 to conduct a left-sided test. So this is a one-sided test to the left. We're looking for evidence that the true population mean is less than 9.2. All right, since it's a left-sided test of the claim that the population mean is 9.2, so when you see left-sided test, we're testing whether that actual population mean is less than this number, so to the left of this number. So this is our hypothesized value of the unknown population mean. This is the sample mean that we get. This is the sample standard deviation that we get. So just like every other hypothesis test, first we gather the information. We have a sample size of 49. That tells us that our degrees of freedom are going to be 48, right? N minus 1. Sample size is 49. Sample mean is 8.5. Sample standard deviation is 1.5. And the alpha level is 0.10. So again, our 4 steps, that's all this is every single time. We form the null hypothesis. Again, it's not an equal sign, it's a colon, it's a statement. The null hypothesis statement is this equation that the unknown population mean equals this hypothesized value of 9.2. And we're conducting a left-sided test, so less than. We are looking for evidence to suggest that that unknown population mean is less than the hypothesized value of 9.2. We list the alpha level of 0.10, and we call it what it is, a one-sided to the left test. Second step, we calculate our test statistic. So this is where we're looking at the evidence, right? This is our t-test statistic. We know the test statistic takes on this form here. Sample mean minus hypothesized mean divided by the sample standard deviation over the square root of the sample size. We calculate that number and we round t-values, remember, to 1 decimal because that's the way the table is set up. And we come out to a value of negative 3.3. And we find the probability that if our null hypothesis is true, remember again the theory here, if the null hypothesis is true, then the center of the sampling distribution of samples of size 49 from that population will follow the sampling distribution with a mean of 9.2. That will be the center of the sampling distribution if it's true. We're taking one sample and saying, well, look, this is, to the left of the center. If this was true, this is pretty far to the left. All right, so we're going to expect to get a pretty small p-value here. The probability of getting something this far away from the center of the sampling distribution of an infinite number of samples of size 49 shouldn't be that far away if this is true. But let's put a number to it. We go to the tables and we say, if this is true, what's the probability that we get a t as extreme or more extreme than negative 3.3? Now, again, remember the table, the t-table is set up for probabilities above the t that we look up in the table here. If I can make this larger. Doesn't really help too much. Anyway, we look up if we want the probability that t is less than negative 3.3, this only gives us positive t values. Again, we know the curve is symmetric. We're going to use 40 degrees of freedom, right? Remember, we have 48 degrees of freedom, so our choices are between the 40 column and the 60 column. So we use the lesser column of 40, and we go down to 3.3, and we can see all the numbers in that row are 0.001. So that's going to be our probability of 0.001 under the 40 column. We come down to 3.3 and we see 0.001. So that's the p-value. That's the probability of finding something as extreme as what we found, the 8.5, if this was actually the truth. Well, again, the logic. If this was true, we would get a value this far away when we take samples of 49 from that population only 1 out of 1,000 times. So that leads us to believe, well, maybe this isn't true, right? Because if it was, why would we only get the value that we got 1 out of 1,000 times? Right? We have already set our alpha level to 0.10 or 10%. So that is much less. The p-value is much less than the alpha level, 0.001, much less than 0.10, or any of the usual alpha levels that we use. So remember the condition: if the p-value is less than your level of significance, you reject that null hypothesis and say there is sufficient evidence to suggest that the true population mean is less than the hypothesized value of 9.2. So just like every other hypothesis test, gather the information, determine what kind of test it is. Are you going to use a z-test statistic? Are you going to use a t-test statistic? Set up the hypothesis, find the test statistic, calculate the p-value, compare it to your alpha, make a conclusion. All right, so I'm going to try to do a few of these examples so that we have many to look at. See you next time.